About ready to listen to Wei Ku's talk. Wei Ku's from Shanghai, and he's going to talk about bad metals and the normal state of cuprates.
All right, so thank you all for being here, and certainly thank the committee to invite me here. This is actually my first time in Brazil. Not my first time in Latin America, but certainly first time in Brazil. And I was actually surprised to see that this institute has all this connection to European and to America. But I would like to suggest that you should add one more connection to Asia, and which is why I add this slide for you. Now, I'm currently both in the university and as well as this institute called Tsung-Dao Lee Institute that just started last year. The end of last year, no, 2 years ago, the end of 2016, we formed a new institute called Institute of TDD Institute. You know TDD is one of the very famous people in China who discovered the parity violation. He got a Nobel Prize together with C.N. Yang, who studied gauge field theory and so on. And he suggested to the president of China that it's time for China to have an institute that is open to the international community so that we can participate the frontier other than just following the hot topic. We want to be a pioneer in leading the hot topic. And it was taken very well by the president of the country. And as a result, we started this institute, which belongs to the government, Shanghainese government and the central government. And we have our first founding director, Wilfried Wilczek, who is well known in the entropy freedom, right? He got a Nobel Prize. And then at the end of last year, he became officially the director. The idea of this institute is not very different from what you have here. It's something like a KITP, right, where you can have people hosting events or programs. So if you want to organize an event like this, but you're tired of staying in Brazil, send us 3 sentences. 3 sentences why this topic is relevant and important, and have a few letters from the community supporting that this is something they will want to participate. Kind of like the KITP operation, but a lot easier. You can come to Shanghai. We pay for everything. We offer lodging and everything. We offer space and everything. All right? So sort of like China is not very rich. They dump all this money to research, but they don't know what to do because they don't have the vision, right? So what we want to do is to share that resource with the community so everybody can benefit, the scientific community can benefit. And the idea is that perhaps this will lead to something great, sort of like the Bohr Institute was able to do when the quantum mechanics was started. In the meantime, we also want to do a little bit of in-house research, a little bit more than KITP, because we don't have UC Santa Barbara to attract people, right? So we need to have some in-house experiment / theory. So we have some kind of mini Brookhaven National Lab kind of design. So the idea is about 500 people, including student postdoc, around 500 people. Okay, so this is something that we will be able to host international conferences, workshops, even programs like KITP program, 1 month, 3 months, and so on. And so you get to invite your friend to go to exotic place like Shanghai and have a good time there. All right, so in addition, for junior members here, we also have junior researcher fellowship, postdoc fellowship, and so on, which you can apply. And this fellowship is pretty prestigious in the sense that you get to be your own boss. You don't work for anybody. You can work with anyone in the institute, right? And finally, we also plan to have a very heavy public education on science because China has a lot of pseudoscience around. They like Kung Fu and all this special ability, which is completely nonsense, but they love it, right? So they're in love in science. But the science they have in mind, not necessarily the science we are talking about in the West. So it's our job as a scientist to educate the community so that they know what truly a science is, starting from scientific method, right? You have to stick to the scientific method. Anyway, so these are the main mission, and I invite you to look into the webpage and also send in your application, or if you're interested, come to China to work as a postdoc. I guarantee you, it will be a fun experience. My postdoc now, one is Indian, one is American. And the American doesn't even want to go back to the US. He wants to stay forever. He's asking me whether he can find a position here so he can stay here. He's enjoying himself. It's too well. I guess too much. A little bit too much. All right. Anyway, so the outline of my talk, I want to talk a little bit about the normal state. So I won't have time to talk about the superconducting feature, although I will quickly glance through some of the important conclusions. All right. So why normal state? Well, if you want to talk about many body physics, you have to start with high energy scale, because imagine that you want to pair a Cooper pair. It makes no sense to say I want to pair a Cooper pair if you don't know what is the quasiparticle in the normal state, right? I mean, you have to pair something. What is that something? You have to understand that, otherwise it's all moot, right? So you start with the high energy Hamiltonian. You have to integrate out the high energy part first before you get to the low energy part. So if you don't know what the high energy physics is, you really have no right to talk about low energy physics on its own, right? Now, of course, that is a bit exaggerating, but that's the whole point of this is that, as we already see from Jagannath's talk, that it is very weird. The normal state is very, very weird, right? And I will show you a little bit, and hopefully I will get you to bring home, maybe not correct, but an entertaining message, that perhaps we are seeing the age of the emerged Bose liquid. And I'll elaborate this a little bit, right? So this talk may be totally nonsense, but I assure you, you'll be entertaining. All right, so normal state of cuprate. This is a phase diagram of cuprate that you already see. This is surrounding dome. And all this region, as you already see from previous talks, this is all unusual. Unusual to the point that you cannot really use any textbook physics to describe the behavior here. When I'm talking about behavior, I mean qualitative feature. It simply doesn't work. In other words, you take the solid state physics book, open the third chapter, do the model, and then from there on, everything else, right? Nothing works, really. Right? That's the point. Now, we don't understand cuprate not only because of the superconductivity. Really, we don't understand cuprate because we don't even know what's going on here. So how do you know what to pair down here if you don't know what is up there? That's the point, okay? So that's why for 30 years, real experts in the field have been trying very hard to understand what's going on here, even today. This, of course, is also important, but we have to understand what's going on here. And let me give you a few examples. For example, resistivity being linear, we already see from Jagannath's data. And I'll show you a little bit of, actually, this is a very limited list. I can, approximately speaking, that everything you know probably doesn't work here from textbook. Right? There are a few things that look okay, but that's an exceptional case. Almost everything you know from textbook does not apply here. So this really is a new kind of material or new kind of state of matter from a solid state point of view. All right. So here's an example. You see something very similar in Jagannath's data, right? Resistivity as a function of temperature is sort of like linear, which is already on its own very weird, because you know from textbook, resistivity should be some higher power, right? It shouldn't be linear, but it's linear very, very well until you get close to TC. Then it turned up this onset, which caused a lot of discussion already, right? In Jagannath's talk. This onset on its own is also very weird. And this is generic. You can see here, this is iron selenide, this is iron-based monitor. And you see the same linear-like behavior. Then when you add magnetic field, this onset starts to get boosted up by magnetic field. This is almost the same as what Jagannath showed us earlier, right? All this behavior, you don't see from standard textbook. In particular, the linear dependence of resistivity is just very exotic, right? This is so-called bad metal behavior that so far has no real solution. Well, there are a lot of proposals, but not real solution. And this is another example. You see this overdope, optimal dope, underdope. You can see that the same linear behavior in thin film. And then here, you see that right before TC, there is always this onset, very dramatic onset. In the longitudinal aspect, this can be masked. But in the transverse side, you see very clearly the same behavior, right? And I will say that this alone is already a big puzzle, not to mention this. Now, some people like to claim this scaling law or being something related to quantum critical behavior. But you can see that this is also different doping. They are far away from quantum criticality, and still this survive. Okay? And not only that, if it's really quantum critical, then it should really work very well at low temperature. But actually, it's the low temperature side that you break down. It is really some kind of intermediate temperature range when it becomes really linear. So again, this is all very puzzling and very weird. Now, but I want to say something more. Look, people study resistivity, but you really should look at the dynamics, because you can get a good resistivity, but totally nonsense dynamics, which means that it's still wrong. You really want to get the low energy Hilbert space right? So you need to look at the dynamics, which means optical conductivity. And if you see optical conductivity, you get something even more exotic. First of all, you see that there is this quasi-Judah behavior whose power law is not Judah at all. Second of all, you see some kind of continuum spectrum. And this is very weird because, one cuprate is a one-band system. Effectively, there is only one quasi-particle band near Fermi energy, and then above it and below it, there is about 1 eV gap. This is the so-called Zhang-Rai singlet and Zhang-Rai triplet states. So there is a 1 eV gap within which you don't have any state. So if you excite quasi-particle excitation or optical conductivity, you should expect to see a gap. Say around here, there will be 1 eV, nothing, right? But in reality, you see it's a continuum. It never dies. It has no feature, but it never dies, which means there are excitation in any energy you impose. But there is a gap here. How do you get excitation in quantum mechanics when there is no state? That doesn't make any sense, but that's exactly what you see here. Right? This is very weird. And not only that, if you look carefully, there is this 100 millieV onset. This onset is in every sample, every doping, every temperature, until a high enough temperature it gets masked by this growing width of the quote-unquote quasi-Judah feature. It eventually gets hidden. But as long as the temperature is low enough, you see this onset in every material, every doping, every temperature. It's the same energy. So it has nothing to do with pseudo gap, has nothing to do with superconducting gap, but it's always there. But the weird thing is that if you look at any Hamiltonian we have, there's nothing of this scale. It's too high to be a phonon, too low to be a spinon or a magnon. It's just a scale that is there, but nobody can identify what it is. Okay? Initially, people think this is superconductivity, but obviously it's too big, right? And the fact that it doesn't change as a function of temperature or doping tells you it's not a superconducting gap. Now, even more exotically, if you now look at low temperature, you open the gap and you go to superconducting states. So you're about to see 2 delta. Some signature of opening the gap, and then you deplete low energy excitation. You never see it. The community of so-called optical conductivity, say infrared people, microwave people, they never see 2 delta. And they don't know why. Okay? You open a gap. How can you not see a gap in the optical excitation? Well, you don't. That's all the exotic behavior that you can see. Now, how do we understand this? Well, I'm going to get back to quasi-particle if I get a chance to do that. But the idea is that, well, why can we solve this problem from first principle? We just start with a full Hamiltonian, let's say multi-band Hubble model, if you like. Let's say we start with a 10-band model, 20-band model, whatever you can imagine. And then you can try to integrate out some high energy degree of freedom, which Anderson did, right? You reduce to some kind of a TJ model by integrating out the double occupancy, which you do know is high energy. Okay, good. Then why don't you continue this? Well, the answer is you no longer have a small parameter, which means that you lose control over what is high energy, what's low energy. You don't know what is the high energy part you're supposed to integrate out, which means that you can no longer drive the system to a lower energy. And that's when we get stuck for 20, 30 years. So how do we solve this problem? Well, Anderson has a brilliant idea. He said, let me just go ahead and guess what's the ground state wave function. I just guess. And if it turns out to be behaving correctly, well, I solved the problem. I don't know how to get there, but I know that what it is. That's how Lafting actually figured out the fractional quantum Hall, right? He doesn't know the Hamiltonian. He just guessed the ground state wave function and turned out to be the correct topology, and he got a Nobel Prize. Anderson tried the same, it didn't work. It's called RVB. Right? RVB didn't quite work, but that's the idea, the philosophy. Well, what we did is something very similar, except that instead of trying to find or guess the ground state, we guess one more thing. Well, one less thing. What we did is that we guess what is the next energy scale where another constraint takes place. In other words, other than integral double occupancy, we want to integrate one more thing so that the low energy effective Hamiltonian are even more restricted to a smaller many-body Hilbert space. And what is that? Well, we guess, right? It's a wild guess. And we guess that you simply, in the regime when pairing is very strong. So if you depair them, it's high energy physics. So you can integrate out this pair fluctuation, So then you wind up having only low energy Hamiltonian that they effectively don't fluctuate anymore. You just have fixed number of boson in the system because you already integrate out the pair fluctuation. Then you wind up having only boson in the system who can or cannot be in the superfluid state depending on whether they condense or not, depending on whether the phases are coherent or not, right? So in essence, you emphasize on the phase fluctuation. So it's probably a reasonable thing to do in the underdoped side. Not so clear whether you should apply this to overdoped side. And I'll show you that the result is so amazingly consistent with the experiment, even in the overdose side, that we are forced to think about maybe this even is correct even in the overdose side. All right, so this is the status of cuprate. We have an elephant in North America, but we don't have elephant in North America. So the natives, the scientists, and the Canadians, we all get around and look at this elephant, and we see all these symptoms, all these very special things, but all we see are horses, right? We know horses, so we start seeing this is a special horse with a kink. It's a special horse of a quantum critical point. It's a special horse of non-Fermi liquid behavior, right? It's a special horse of a Fermi arc with a charge stripe. We pretend it's a horse, and here horse means BCS theory, right? We pretend it's a BCS theory with all these very special features. But someone from India came and said, well, look, guys, this is just a standard elephant. There's nothing special about it. You just think it's special because you misidentify that to be a special horse. This is really a normal elephant. So our job as a scientist is to find out that this is really not a Fermi liquid, rather it's something new. And that something new has all the generic behavior of all these features. So we don't need 5 different theories to explain a kink. We don't need another 5 different theory to explain a non-Fermi liquid scattering rate. And we certainly don't need another 5 different theory to explain the Fermi arc. At the moment, that's the status of the field. That is, we try to explain all these symptoms and explain them one at a time. And most of the time, whatever you use to explain one does not really directly affect the other symptom, right? So we are trying to understand what's going on. Now, in this talk, I'm going to try to show you that there's one crazy idea that I myself has not fully convinced myself is correct, but this crazy idea, which I just explained to you, turned out to explain many of these features in one Hamiltonian, one set of parameters, and you get almost quantitative agreement with experiment in more than 5 or 6 different observations already, right? So it could be that this crazy idea is not so crazy, and if this is true, we are really seeing another solid state that is different from Fermi liquid. And this is what we call the emerged Bose liquid. All right? So, okay, I need to speed up a little bit, so I will just quickly. Okay, so for example, this is the, I'll skip that. Well, why, when I said that the normal state is always very strange and so on, let me first show you in this phase diagram, in the superconducting state, for example, here. You will see that in this region, you have a good superconductivity, and you have this nodal quasiparticle that you can measure. If you estimate what's the entropy, you can do that in elementary school exercise for students, right? Any undergraduate student can do it. You will find that you get t squared for a quasi-2D system. The specific heat should be t squared. And the experiment show you something like t to the cube. Okay? So how can you, having clearly a quasi-particle, so you must have a contribution from that. You can add that to the entropy. Of course, you can have something else, but you keep adding them, right? You don't subtract them. There is no interference in counting states. So you just add them. How can you have t to the square that is invisible from experiment? It's not possible. If you see t to the cube, you cannot hide t to the square, because if you go to small enough t square must be infinitely larger than t to the cube. You can't see it. You have to see it. And you never see it. How can you not see it? You do see a quasi-particle, but you don't see its contribution in statistics. How is that possible? Well, if you accept the fact that these quasi-particles you see are not weighted properly, meaning that they have a negligible small amount of weight, all the fermions in the system that are already gathered around forming boson, so they don't participate in these statistics, then you actually get to the cube, right? For example, just a simple example that the idea is simply that the emerged Bose liquid actually might be the right way to look at the normal state. So here, I'm going to skip the model because it's actually very, very simple. You just have a 2 fermion forming a nearest neighbor tightly bound pair. and you assume that they bound so strongly that they behave like one boson sitting in the middle, and then this, of course, this boson form a checkable lattice. Now, surprisingly, this checkable lattice has all sorts of weird pathology. That's so interesting, because the lower energy part is 3D, but the high energy part has a degeneracy, so it's 2D. So it has built into the Bain structure a frustration and competition and interdimensional crossover. This model is so amazingly simple and interesting. We didn't realize it until we studied them, right? So just take this model. It looks nothing but a simple type bonding model with some kind of hardcore constraint. And if you look at this and map it to a spin Hamiltonian, this is an unsolved problem that people believe there might be a spin liquid. Okay, this is a simple model that is built, has a built-in frustration in the entire half phase diagram. It's not just the point. Half of the phase diagram are frustrated. So it's a very interesting model. Now, I'm going to use that model to show you something very simple. This is the Bain structure of that model. It's intrinsically two-band because there are two different sides, right? Two different bonds. And then if you look at the density of state, you look at this. This is a quasi, well, this is a 2D density of state. I'm plotting here 2D. So you see the 2D feature. But then here you see the quasi 1D feature. That's what I'm telling you. This system has interdimensional feature. The bottom here, if you go to a 2D system, is 2D. But here is actually 1D. If you go to a 3D system, then here, bottom here is 3D, and this part is 2D. This is very, very important, okay? Now, if you take that and simply just say, oh, okay, now let me add the electric field, because this boson carries charge. It's a charge boson, therefore it will flow. So I just use the Cooper formula to calculate its optical conductivity, and this is the result, right? Of course, the important thing is that these are bosonic lines, which means this really corresponds to a four-body correlation function in the fermion channel, which nobody studied. That's why you miss this physics completely, because we only studied two-body correlation function. This is a four-body correlation function, which means the two-body correlation functions are now high-energy object. So the low-energy object, the only relevant one is this four-body term. If you do that, this is what you find. You find this behavior. You find, first of all, continuum, which I would already emphasize is extremely difficult in fermion channel, nearly impossible. Now it came out. You see this quasi-Juder, which I will not emphasize today. But then you also see this onset at 100 millieV. And this is all very uneasy to understand. The reason there is a continuum is because you see here, I have two bands, so naturally I can have inter-side excitation, inter-band excitation that is continuous. There is no gap, right? So naturally you get a continuum. And you see this 100 millieV onset, very, very trivial, because they are actually in this model two for a whole singularity. And this excitation is exactly 100 millieV. So you get this dynamic feature trivially out of this boson, all right? Now, I will quickly go through the doping dependence. As you do more and more, the spatial weight grow, as experiments show. Obviously, some rule will dictate that. As you lower the temperature, you see that the low energy part actually, when you lower the temperature, or maybe here I use the raise the temperature, you see that the high energy part increase, the low energy part decrease. This is exactly what you see experimentally as well, all right? So, most amazingly, now you take the zero temperature limit, zero frequency limit, which is the DC conductivity or DC resistivity, and you plot that as a function of temperature at different doping. You see, from overdope or optimal dope to lower and underdope. What you see is that you see a linear resistivity, which I already told you is very hard to generate, but it's trivially come out of a bosonic statistics. This is just boson. It's linear. And you see, as a function of doping, the slope change. This is sort of remind me of this field dependence that you were talking about, but this is doping dependence, but same thing. You see, the slope is changing, but it's in the same way. Experiment is seeing the same. But wait for the most amazing part. We can do this analytically. So we have a formula. Resistivity is something like 40 times sin square of this. So at high temperature, when this is almost zero, this is a constant, you just see a linear part. But when you get close to TC, the low temperature physics start to come in, the sinh square start to take off. And what you see is that you see this onset, which we discussed a lot in the previous talk when Jorgen and I talk about it. You see this onset, this is universal. And this is actually very similar, this is TC, right? So it's very similar to what seen in this other measurement. right? And this, what you usually call the superharmonic fluctuation or vortex, it's not. It's just intrinsic boson. Bose liquid behave this way, period. Nothing special. This is intrinsic. Any Bose liquid behave this way. It comes from Bose-Einstein statistics, period. Nothing special, all right? So, you see, I show you.
Do you actually mean Bose gas? Because you do the calculation in a gas.
Well, of course, the calculation is gas, but in reality, there is a hardcore boson. There is an interaction whose effect will be important once you go to the condensed state, right? But of course, in the normal state, it's not important. All right, so I'm running out of time. So the point is that, you see, I show you that this emerged Bose liquid is able to generate this, what we believe to be almost impossible fermionic behavior, because they start to become different statistics. Now, if you now say, well, what happens if you cool down this system to below TC? Well, this is this paper that we published. It turns out that at overdose side, or at higher than 5% doping, there is a single minimum here that you will have from BEC, which means you will have a superfluid. But when you go below 5%, surprisingly, this quasi-2D part that I told you about, the lower dimension part, becomes the lower energy. There is a level crossing. As a result, you lose capability to condense, which means that even though it's boson, if the doping is low enough, the kinetic energy changes to the point that it will not condense. It is not in the standard way that a single momentum will become condensed. It will not happen. So that means that you will lose the capability to maintain superconductivity, and even though it remains a boson. And what this happens is exactly this 5%, what we call the quantum critical point at the end of the dome. And what happened there is that the effective mass of this boson diverge. So you no longer can have a phase coherence. Now, it's interesting to find that this is exactly what you see in the experiment here. In this region, there are many things that is weird. For example, you will find that, well, don't get into that. So the idea is that if you not have an interference, that you can have a mass divergence. And once you have that, okay, so now can we have evidence? Well, this is superfluid density as a function of a TC, meaning that you look at very close to underdome dome, you look at the correlation between TC and superfluid density at zero temperature, and you anneal the sample a little bit to change the doping a little bit, and then everything moves, right? So every data point here is one annealing. It's same sample, different oxygen concentration because of annealing. Then you see that this is supposed to be a linear line, but it's not linear. The slope here is flat. The green one, the blue one is a theory, and the red one is an experiment. You can see very clearly this flatness indicated that mass divergence. This is already confirmed by this experiment. Now, there are many things you can look at near under this critical region. There are many things, like, for example, superfluid density or penetration depth is like 2 orders of magnitude longer than you expect from the experiment. Okay, but this is easy to understand once you realize the mass diverge. The mass is heavy, very heavy. You also see the, for example, isotope effect. There are many things, but I'm not going to talk about this in detail. Now, one last thing I can show you is, look here. This is superfluid density as a function of temperature for different doping. This is the same data point when they anneal over and over again. Okay, what you see very strange is that at high doping, say 7%, this is underdoped system, you see this order parameter having some kind of fractional power law, right? This is the typical mean field-like behavior you expect. But when you get close to quantum critical point, it becomes a straight line. So the critical exponent here is roughly of order 1. In other words, this is a system where the exponent change as a function of doping is not universal anymore. Okay? Now, surprisingly, using the same model, we calculate the green, red, black. So these blue ones are the experiment, and the green ones are our theory. You can see that at overdope, at high doping, 7%, and then as you get closer and closer to this 5.2, this is 5.2, sorry, then you become more and more straight. So you are, even in this simple theory, changing the critical exponent continuously. Exactly how, we are still investigating on that. And you can also calculate the critical current simply using the superfluid velocity as an estimate. And you see that it has this behavior that is going downward and upward. There is a change of curvature in the theory, and you see that in all the experiments we can find, You see the same change of behavior. So not only we get the ground state right, we get also the low energy excitation right. So now we are systematically checking the entropy, we are checking the critical behavior, we are checking everything we can find. So far, it seems that everything we check work out. Now, I don't have time, so unfortunately, I have to skip the rest of the talk. I encourage you to look at for this paper where we show that in this case, the superconducting gap you get is actually not the Bogoliubov quasi-particle excitation. In the BEC limit, there is a second kind of superconducting gap, which has a slightly different form. Okay, and that form deviate from the order parameter at some momentum region, and you compare very well with the ARPES measurement. All right, so not only you have a BEC, you also have a BEC gap, which is different from the BCS gap. And this is already on the archive, so I won't talk about it, just tell you what it is. You can find this on the archive. Now we look at the quasi-particle excitation of fermion, which is measured by ARPES and STM. And what you find is something very surprising, that it explains the non-Fermi liquid behavior, namely at zero frequency, zero temperature limit. Fermions supposed to have no lifetime, right? Infinite lifetime, meaning no dissipation. That's just coming from the fermionic particle principle. It turns out in the experiment, you always find finite dissipation with linear dependence in frequency and temperature. This is non-Fermi liquid behavior. Second of all, you also find there is always a kink in the dispersion. And then, more amazingly, you also find the scattering length or the width of this dissipation you measure at above Tc somehow is proportional to the superconducting gap at low temperature. So somehow what's causing the dissipation at normal state is related to what's causing the gap in the superconducting state. These are all related. And then you can quickly go through our model the same way, figure out the scattering of this boson. When it's above Tc, it's incoherent. You scatter them, you get a width. When it's below Tc, you scatter them, it's coherent, then you get a gap. So naturally, they are proportional to each other, very naturally. And what you find is surprisingly, the self-energy you get has a finite dissipation at zero temperature, zero frequency limit. That comes from the fact that boson at zero temperature limit always have fluctuation. Not only that, but you can see this self-energy is consistent with experimental observation. These are experiments. You see the two peak feature, we see the same thing. Not only that, but you also see there is a kink because of this feature. The real part has some change, and that kink, this is experiment versus theory. One is experiment, one is theory. You see, the kink is the right place. So we were not trying to figure out the kink. We were only trying to see what's going on if you scatter and the boson. It turns out it gives you both. Now for liquid behavior, it also gives you a kink. Not only that, it also gives you a scattering, or so-called alpha square F, the density of state of a boson, looks very much like experiment, right? In fact, this arrow I put there, they only focus on this one. But since we have a Van Hoff singularity here, I looked for it and I found there is some very tiny signature that look like what we have here. And we also produce all this dependence or this correspondence between the normal state and the superconducting state. It's trivially obtained because of this relationship that they scatter against the same thing. So to end, I want to tell you that we have a very crazy idea that the system is now a emergent Bose liquid. In other words, we can safely ignore, for most purpose, a fermionic degree of freedom. And it turns out this crazy idea seems to produce many characteristics of the system, even semi-quantitatively. Not just one. We have one Hamiltonian, one set of parameter. We apply to many observations, and they seem to capture the right characteristics. So if this is true, well, I'm still not convinced. I need to do more, right? I want to calculate everything and see how many of the characteristics we can capture. But if it turns out this is true, if it continues to be true, then what this really tells us is that we have been studying Fermi liquid. That's the solid state physics. Now what we need to do is to take the first chapter, replace that by a Bose liquid, and we derive every chapter afterward. We now have a volume 2 of Ashker Mermin, and that's what cuprates is telling us, that the world is composed of Fermi liquid and Bose liquid. We just didn't know. We've been staring at the Bose liquid for our life. We are learning that it is a simple Bose liquid. Now we need to finish the second chapter, second volume of the solid-state physics. Then we're done. All right, thank you.
Okay, thank you. Are there any questions? Okay, I have maybe an obvious question. I should not do it. So if all the fermions are paired, how come we can see low, like basically zero energy fermions?
Very good question. I don't know the answer of that. I do know that if you add, just say you have a bunch of fermions that already form bosons, tightly paired boson. You inject a fermion to the system, you can still see the spatial function. The problem is that you probably expect a very large gap. So the question is, how do you pin the chemical potential? I don't know the answer to that. I do know that the boson actually are composed of fermions that are indistinguishable from the photon hole that we inject from ARPES and STM. Right? What we did is we add one more hole to the system and observe how it propagates. So that's what we measure. I do know that you can have low energy excitation, but what I don't know is how you pin the chemical potential, because it turns out they are not they are indistinguishable. So the bosonic operator and the fermionic operator do not commute. So in this case, I really don't know exactly how to treat the chemical potential of both subsystems. This is a question we are still trying to sort out.
Thanks. There a question here?
Yeah, so to follow up on Luke's question, let's say that this was S-wave, and I were to start with some saddle point. This is nausea Schmidt-Ring, I don't know how long time ago. As long as you're not at half filling, the chemical potential drops below the bottom of the fermionic band, and so then...
You'll be in the gap, right?
The chemical potential gets renormalized, so now you have to renormalize both the gap and the chemical potential. It drops below the bottom of the gap band, and so then that's how we would describe the Bose
for pure
gas.
But if you now add one more, you add a photon hole to the system. One body green.
No. So let's just do thermodynamics, right? So then, if it's D-wave,
the question is that you can see the fermionic band from ARPES and STM.
Yeah. So let me just pose my questions. But so if this was D-wave, as long as again I'm not at half filling, the same thing would happen. In strong coupling, the chemical potential is going to drop, and you're going to have a hard gap for fermions. So say that I apply magnetic field. Magnetic field is not very strong, and I measure the heat capacity as a function of magnetic field at low temperature. I would get square root of H experimentally. How does one recover something like that here? That's thermodynamics.
Hold on, I'm not following the square root of omega part.
Square root of H.
The square root of H part. I'm not following that.
So in the fermionic language, is explained that you have Doppler shifted quasiparticles, and the large Dirac quasiparticles near the D-wave nodes.
Yes. Yes.
Right. So the higher the field, the stronger the superfluid gradient, and the larger the Doppler shift, and so you're getting square root of H.
Yeah,
that's the Volovik effect.
Right.
So I don't see how that's going to happen in a situation where fermions are completely gapped and the only player is the hardcore boson.
Well, again, I'm saying that I don't understand how you can pin the chemical potential properly, but I do know that experimentally, you do see the quasiparticle, but at the same time, the quasiparticle seems to carry no weight in a specific heat, right? I already make it clear that the specific heat should be T squared once you have a 3D Dirac cone when you are in the superconducting state. Right? You can calculate this. T squared. No. Experimentally, in the underdome side, it's T to the cube. Now, in this case, it's T to the cube. I had the data, right? I show you the data. And that's the part that is really puzzling. We do know there are quasiparticles, but they don't seem to contribute to the statistics.
Everybody except for maybe one paper by Hai-Hu.
As far as I know, every experiment except for maybe one paper by Hai-Hu in the Bisco sample C over T versus T squared have a finite intercept.
Yes. So there is indeed, you're right. There is a T linear part. There is also a T to the Q part, but there is no T squared
that's
part.
phonons.
Right? But there is no T squared part. The point is that you cannot get away from T-square part. You have to have it, but you don't. You have a quasi-particle that form a Dirac cone. If it has any statistical significance, it will give you a contribution of T-square. You cannot escape from that.
If it's clean, yeah.
But you never see it. That's the problem. So there are a lot of ways about quasi-particle excitation of single fermion. There are a lot of questions. I don't know the answer. Okay? But what I'm saying is that that's the overdope side, right?
Yeah, C over T.
Right. But if you now go to the 10% doping, right? The 10% doping is not that exotic, right? It's just underdope. But you can see already C over T shows something like a square, which means that C is T to the cube. Right? This is not a linear line. There is nothing linear here. It's just a square.
So the physics is to do with the underdoped, with all the physics you're claiming.
Physics, of course, slowly.
Is for the underdoped side, and you're not accounting. You don't have a theory of the superconductivity of the overdoped side.
I am actually saying something different. I'm saying that here in the underdoped side, you clearly have a dilemma that this quasi-particle excitation we see from ARPES and STM don't seem to matter in the statistics. Maybe they become matter in the overdope. I don't know. I'm just saying that in the underdoped side, there is clearly a contradiction. Yeah, that's what we said. There is a linear part and there is a T to the cube part. There is no T to the square part. But any Dirac cone should give you T to the square. And nobody has seen that, as far as I know. So I'm not saying that I understand how to explain this. I don't even know how to pin the chemical potential. As you said, there should be a gap. Right? The chemical potential should be way off. I don't know the answer to that. But I'm saying that at the same time, nobody knows how to explain this either. So at the moment, I'm just saying that let's just take a leap of faith. Let's pretend, as far as most physics is concerned, these fermions are less relevant in this region, and see what happens. If they describe 90% of the physics, I'm satisfied. Then we will eventually have to figure out the fermionic part.
Okay, so I think this is a good point to thank Wei Ku again. Yeah, our next speaker is going to be Amit Gosal from Kolkata, and he's going to talk about disordered vortex lattices.
Yeah, so let me check if I can get this thing right.
The talk is supposed to be 30%, so I'll do the
Okay, so what's that?